Okay, guess we have another snow day. So let me give you the notes for the first part of section 4.4 in your textbook. Okay, here's our basic starting point. If you have the antiderivative of a derivative, not just the antiderivative of some random function, but I know that this is the derivative here, and I'm going to take the antiderivative of it, it's going to take me right back to the original function. And you get a plus c. Okay, this is pretty straightforward. We're now going to look at what to do when we want to do a definite integral under these same circumstances. And it's really pretty easy. If you take the antiderivative of a derivative and you evaluate it from a to b, you just find the function f of x, take the antiderivative, and then you plug in b, then you plug in a, and you subtract. It's really very simple. This is called the fundamental theorem of calculus. Now, considering it's called fundamental, you probably consider that's pretty important. Okay? So there's also another notation for it. I'll show you as I work through through several of the examples, the way that we write this work down. So we're going to take a function, 3x squared plus 2x plus 1, and I want to take the definite integral of this function, 3x squared plus 2x plus 1, and I want to evaluate it from 1 to 3. All right? So the first thing you do is just take the antiderivative, the way that we already learned how to do it. The antiderivative of 3x squared is x cubed, and then plus x squared, and plus x. And we get a plus c, and I'll show you what's going to happen to that in a few minutes. This is the notation that we use right here to show that we're still doing a definite integral. You put a box on one end, a bracket on one end, and you write those numbers 1 and 3 right here. So you've already taken the antiderivative, so we don't want to have that little curly s thing anymore. You just put this box. I've seen some books that just put a vertical line like that and put the 1 and the 3 on it, but most places actually do a little box like this. Okay? All right, then the next thing that you do is you plug in the 3, the top number, and then you plug in the 1. Watch your use of parentheses, and then you've got a numerical answer here. You do all of your arithmetic here, and you're going to get 39 here, plus c. And on this one, you're going to get 3 plus c. And what you want to notice is that you're going to get a plus c here and here. That's going to happen every single time. So every single time that you do a definite integral, the c values are going to go away, and that means that we're going to quit doing them. We're not going to keep writing it in there. You can leave it if you want to, but most people just leave it off when you're doing definite integrals. We end up with the answer 39 minus 3, and this answer is 36. Now, we did these with our calculator last night, so on any of these problems, if you want to double check your answer using your calculator, that'll be just fine. So let me just punch through a couple more examples so you can see how it all works. The integral from -2 to -1. It doesn't matter what variable you use. Right? As always, you want to stop and consider if you need to rewrite your function to make life a little bit easier. So this time I'm going to change these into u minus u to the -2. I'm going to take the antiderivative of u, which is 1/2 u squared, and then the antiderivative of u squared, u to the -2, sorry, u to the -1, and the reciprocal of -1 is -1, so that becomes plus 1 right there. And here's my notation that says, and I'm going to plug in these two numbers. All right? One of the most common mistakes on these problems is messing up on this next step with subtraction. So keep in mind that you're going to have two things to write down. You're going to have to put this entire piece in this set of parentheses and also in that set of parentheses. And just keeping up with everything. How much work you write down is, of course, up to you for arithmetic. I went ahead and changed that 1, u to the -1 to 1 over u. 1/2 -2 squared plus 1 over -2. So I changed it. I guess I should have written this down in here. Plus 1 over u. -2 to -1. That would be a little bit better. And you know, I know you're gonna want to pull your calculators out, but keep practicing these little bits of fraction arithmetic. They're just gonna make you better at your fraction arithmetic. And sometimes nice things happen. Like this is a 1/2, and a plus another 1/2, so that's 1. 1 minus 1 goes away, and the answer is -2. Okay? Another one. Variable from 1 to 4 of 3 square root of x dx. Which I'm going to rewrite as 3x to the 1/2. You can pull the 3 on the outside, or you can leave it on the inside. That's pretty much doesn't make any difference. If it's really complex, I usually pull the constant out. Okay, 3, and the antiderivative of x to the 1/2 is x to the 3/2, and then times 2/3. And you notice I'm leaving the plus c off. I forgot to mention that on the last one, but every time you do this, the plus c is going to go away, so you might as well just leave it off. Okay? And I do like to simplify my expression before I start plugging the numbers in. You can plug the numbers in here, or you could go ahead and multiply your coefficients and plug the numbers in. Okay? All right, so 2x, times 4 to the 3/2 minus 2 times 1 to the 3/2. Okay, so the first one, the top number, and the bottom number. So I picked this example because I wanted to make sure you remembered how to do 4 to the 3/2. That means the square root of 4 cubed, or the square root of 4 cubed. Either one of those things, whichever one looks easier, will work. This time I'll do the square root of 4 is 2, cubed is 8, so 2 times 8 is 16. And of course the 1 to the 3/2 is just 1, and so my definite interval here is 14. Okay? I'm going to give you several examples that look similar to your homework, or to some of your homework. Remember that you want to look at the function first. We don't have any rules for taking antiderivatives of quotients. So you need to look and see if you can rewrite that quotient, and you can. That'll be 2x to the -2 minus x to the -3. And then take your antiderivative. Be careful with your signs. 2x to the -1, and we'll have times -1 minus x to the -2, and we'll have 1 over -2, so that'll make that a plus. Just watch out for your signs. This is evaluated from 1 to 2, and I just really like to clean this up before I start putting numbers in. 1 over -1 over 2x plus, I wrote that wrong, sorry. -2 over x plus 1 over 2x squared. I just find it easier to plug in after I have rearranged this. Got rid of those negative exponents. Okay? So again, this has got a plus in it right here, and sometimes people just forget that they've got to do the whole thing twice with the 2. -2 over 2 plus 1 over 2 times 2 squared, and then -2 over 1 plus 1 over 2 times 1 squared. You plug in the top number, you plug in the bottom number, and you subtract. A little bit more fraction arithmetic. -1 plus 1 over 8 plus 2 minus 1/2. Change everything into eighths. 8 eighths plus 1 eighth minus 4 eighths gives me the answer 5 eighths. Okay? And one quick trig one. So you notice that 0 to pi over 4. It's pretty common on the trig ones for you to have trig numbers as your integration values here. Okay? We kind of, hopefully you're still remember all your antiderivatives of your trig functions, but just stop and think, what function has a derivative that is secant squared? The derivative of tangent is secant squared, so the antiderivative of secant squared is tangent, evaluated from 0 to pi over 4. So I write tangent of pi over 4 minus tangent of 0. I don't really need those parentheses here because there's no pluses or minuses, but it's going to have to be in. Then you have to make sure you haven't forgotten how to find the tangent of pi over 4. Unit circle, triangles, graph, whatever you use, tangent is 0, and that gives you a definite integral of 1. Okay? You will have a good little handful of problems to work where you just are practicing this antiderivative definite integral process. Okay? And then there's going to be some other ones that are a little more application based. If you have a derivative, that is a rate of change. Remember that a derivative is a rate of change. If you have a derivative or a rate of change as a function, okay, then when you do a definite integral, when you do the definite integral from a to b of something that is a derivative, it's going to take you back to the original function. Evaluate it from a to b. And what you get here is an amount of change. How much something changes. That's going to be sort of critical to some of the application problems that we're going to have over this unit. So let me give you one quick example with velocity. So I have a velocity function here, a nice simple one. And we've already done this. If I said find x of t, you would take the antiderivative of the velocity. Antiderivative of 4t plus 1. And there it is. There's the indefinite integral for the antiderivative. And then if I said find the position at time 3, that's x of 3, which is plugging 3. Which gives me 21 plus some unknown constant. And if I said find the position at t equals 1, that's x of 1. And if I ask you to find the change, the amount of change in position from t equals 1 to t equals 3, and that's x of 3 minus x of 1, which is 21 plus c minus 4 plus c, which is 21 minus 4. Did I add wrong? I did something wrong. This is supposed to be a 2 right here. I apologize. That makes this a 3 right here. Okay, I copied this wrong. Right there. All right, so it becomes 21 plus c minus 3 plus c, 21 minus 3, which is 18. So the amount of change in position. And this is all perfectly good work, and there's nothing wrong with it. But you could also show it this way. If I said find the change in position, and I've got velocity, and I can simply do the antiderivative of velocity. That's going to take me to position and evaluate it from 1 to 3. It's going to give me the exact same pieces of information, but all in one clean step rather than being in several separate steps. I'll take the antiderivative of 4t plus 1, I get the same thing that I got before. Okay, I can leave the plus c off, evaluate it from 1 to 3, and then I do exactly the same thing. It's just all in one clean, concise step rather than being in several separate steps. Okay. All right. So we'll see some more applications a little bit later on. All right. A little recall. This is the mean value theorem. The mean value theorem says that the actual slope of the tangent line is somewhere going to equal the slope of the secant line. Okay, so let me write that again. This is the slope of the tangent line. And this is the slope of the secant line. And that's the endpoints. And that C value is going to be somewhere in between the A and the B. Okay. In terms of application, this says the actual rate of change, or maybe a better word than actual would be instantaneous. How fast is it changing right now is equal to the average rate of change. Okay, this is old. This is called the mean value theorem. Okay, there's a second mean value theorem. It's called the mean value theorem for integrals. And this is what it looks like. The definite interval from a to b of f of x dx is equal to f of c times b minus a. This is just a guaranteed existence, okay? Guarantee the existence of this value of c, all right? And just looking at a simple graphic demonstration of this. Here's this function f of x from a to b, right? And what it guarantees to you is that this area, remember we talked about this as being area under the curve, can be found by looking for a rectangle that has the same area. Here's the b minus a, and the height of this rectangle is f of c, where c is this value right here. So the area under the curve can be found by finding a related rectangle where the c value is somewhere in between the a and the b values. Now, I usually prefer to write this theorem this way. Okay, it's the same thing. If you go back and look at the original way that I wrote it, this right here, this. You just divide both sides by b minus a, then you get this statement right here, f of c equals 1 over b minus a times the definite interval from a to b of f of x dx. All right, this is called, this right here is called the average value of f. Okay. Now, when we talk about average values, when we talk about finding an average of something, we usually think we add something up and divide. And this is kind of that same concept here. This part right here, remember, is an infinite sum. It's the limit as n approaches infinity of the sum. It adds up a bunch of things. How many things? An infinite number of things. We're going to add up all these things, and then we're going to divide it by b minus a. And that's going to give us the average, okay? So we say that this is the average value of f. We say the average value is the y value, and it occurs at the c value. Okay? Let me give you an example. Find the average value of f of x equals 3x squared minus 2x. You know, that's got lots of values. Every time you plug in a different x, you get a different value for f of x. And I want to find the average value in between 1 and 4. Okay, over that value. So it's basically you're going to add up and divide. That's exactly what we're going to do. Okay, f of c equals 1 over b minus a times the interval from a to b of the function. How do you find an average? You add up a bunch of things and then you divide. Okay, the average value of the function. So let's add up all of the values. We change this to 1/3 by taking the antiderivative. of this function, or actually just grab your calculator and do this, that'll be a little bit faster. Just go ahead and do this on your calculator, just to get the practice. And you can pause and check and make sure you get the same thing that I did. I got 48. You do that by hand. It certainly can be done by hand, but you can ask them to use your calculator on that. And that gives us that 1/3 times 48, or 48 divided by 3. The average value of the function is 16. Okay? So the function f of x equals 3x squared minus 2x has lots of values. It has f of 1, f of 2, f of 3, f of 4, f of 1.5, f of 9, f of 1.9, f of 3.6. All of those are values. But if you add up every single value, that's this, add them all up and divide by 1 over b minus a, you get that the average value is 16. The second question is find the value of x that corresponds to this, or find the value of x that corresponds to this, and that's usually worded this way: find the value guaranteed by the mean value theorem for integrals. And that's not hard, that's easy. All you have to do is take f of x and set it equal to 16 and solve for it. Well, sometimes it's hard, but it's not usually not too hard. 3x squared minus x equals 16. And again, for purposes of these notes, I'm going to skip over solving that. I don't know if that solves my factoring. I can't really remember, but you can certainly do it on your calculator to find the value that is guaranteed right there. Okay. All right. Another kind of an application. I'm going to draw a graph that shows the velocity. Okay, so here's a graph that represents the velocity of a function. Okay. And the question is going to be, find the distance traveled in the first 10 seconds. And that means from 0 to 10, not from 1 to 10, it means from 0 to 10. Okay? All right, if you have velocity, you want distance, you're going to have to go backwards from that. The distance traveled, so we need an antiderivative of the velocity. That's going to take us back to the position function. And since this graph is always positive, because the graph is always positive, then we can just evaluate this from 0 to 10. Because when I get this, take this antiderivative, it's going to take me to position. Then I'm going to plug in the 10, and I'm going to plug in the 0, and that's going to tell me how far it has traveled. Okay? I'll give you a second picture of velocity. And this time we have some positive velocity and we have some negative velocity. Okay? Here, positive velocity, and here we have negative velocity. Okay? So this time if I ask you for the distance traveled, you're going to have to do the antiderivative from 0 to 2 of the velocity. That's going to give me that positive piece at the top. You're going to have to do a separate piece, the antiderivative from 2 to 5 of the velocity. This is going to give me a negative number because it's below the x-axis. And distance is always positive, so we can't have the distance traveled of having negative numbers in it, so we're going to counter that by putting the minus here, just like we did when we did areas. If you did this, if you just found the antiderivative from 0 to 5 of the velocity, you would, in fact, get a number that has meaning, but it's not going to be the distance traveled, it's going to be displacement. In other words, it takes into account where you started and where you ended, and it pays attention to the sign. Okay, so you moved in some positive direction and you moved in some negative direction. All right? If I asked you to find the average velocity, if I ask you to find the average velocity, this is the same thing as the average value of velocity. We just did average value. The average value is 1 over v minus a times the integral from a to b of whatever function you're asked to find the average of. This time it's of the velocity. So the average velocity based on whatever your picture is going to be 1 over, for this problem I was just doing it 1 over 5 minus 0, the integral from 0 to 5 of whatever the velocity equation was. Okay? And if I had some area information, if I knew the size of this area here and the size of this area, then I could evaluate this definite integral by using those areas up above. Okay? All right. A couple more quick things in the application format. Some more problem number. That's all on. Okay. Let's suppose that I give you E of t, and I tell you that that's the rate at which people enter a mall from 9 a.m. to 5 p.m. Okay, I'm going to give you some function, and this is a rate of change, how the rate of which people are entering the mall. The units on this is going to be people per minute. Then I'm going to give you another one called L, and this one's going to be the rate at which people leave the mall again from 9 to 5. And these units are also people per minute. Okay, so I have two functions. Okay. One tells me how fast people are coming in, and one tells me how fast people are going out. Right? So I want you to take a look at this function. Which adds those two functions together. We'll subtract them. Okay? What does this function represent? This is the rate of change. Of the number of people in the mall. It's taking into account how many are going out as well as how many are going in. Okay? This is just how fast the number of people in the mall are changing. Okay? Now, if I tell you, if I say that there are 150 people in the mall at 9 a.m., beginning of this problem. That's an initial value. How many people are in the mall right when we start? Okay? Then, if I take 150 and add to it the rate, I forgot to ask the question. If I ask the question first. And I want to find out how many people are in the mall at noon. Okay? Well, there were 150 people to begin with. This equation tells us how it is changing. It tells us a rate of change. We have a rate of change and we want an amount of change. We take the antiderivative. Take the antiderivative of the rate of change and it gives us an amount of change. So we start with an initial value plus an amount of change. Now you're going to have to know what the change is from and to. Well, we started at 9. I'm going to call that 0 instead of calling it 9. And we went to 12. So if 9 o'clock is 0, then 12 o'clock is 3. And it'll just be easier for me to take the antiderivative from 0 to 3 than from 9 to 12. Okay, now tell me how many people are in the mall at 12 o'clock. If I wanted to know how many people are in the mall at 5 o'clock, it's exactly the same process. 150 plus the antiderivative of the rate of change, how fast it's changing from 0. And then we're going to go to 5 o'clock. But remember, you're starting at 9. So from 9 to 5, if that's going to be 0, then 5 o'clock is going to be 8. And that'll tell us how many people are in the mall at 5 o'clock. All right? All right, and I think that's it. Some of your homework tonight, you're going to be doing these definite integrals analytically. That means without a calculator. And some of them you may do with the calculator. Do a little bit of practice with both, and you'll be in good shape when we get back.